to The Explainer. Today, we're diving into the world of capacitors. These are the unsung heroes of modern electronics, and we're going to get right into the key formulas that make them tick. We'll see exactly how these equations help solve real-world engineering challenges. Okay, so here's the game plan. We're going to start with the basics, what even is a capacitor, then we'll dig into the math behind calculating capacitance itself. After that, we'll see what happens when you put them in circuits, figure out how much energy they're packing, and wrap up with a cool trick to boost their performance. All right, first up, what exactly is a capacitor? Let's get to the bottom of it. You know, at its core, a capacitor has one main job, storing electrical charge. Think of it like a tiny battery, but one that can charge up and discharge, bam, in a split second. That's the magic behind your camera's flash or countless other things inside your phone.
Okay, now this is a classic mix-up. It's super easy to confuse the symbol for a capacitor with a battery. But if you look closely, the difference is simple. The capacitor has two parallel lines that are the exact same length. A battery, it's got one long line and one short one to show you which side is positive and which is negative.
And this simple fact right here, it's the absolute foundation for everything else we're going to talk about. It basically says the more voltage you push across a capacitor, the more charge it holds onto. It's a straight-up, direct relationship, and that leads us to the most important formula of all. And here it is, Q equals C times V. Seriously, this little formula is everything. Q is the charge, V is the voltage, and C is the magic number. That's the capacitance, and it tells you how good that specific capacitor is at storing charge for a given voltage. It's kind of like its defining stat, and we measure it in farads. Okay, so we've got this key relationship between charge, capacitance, and voltage, but let's get practical. How does the actual physical shape of a capacitor, its construction, affect its ability to store charge? Where does that C value come from? Well, the cool thing is we don't have to guess. It's not just trial and error. We can actually use a couple of fundamental physics principles to derive a formula that links a capacitor's physical size and shape directly to its capacitance. It's pretty awesome. Okay, stick with me here, because this is where the magic happens. This looks a little intense, but the idea is actually really elegant. See, we've got two completely different ways to describe the electric field between the capacitor's plates. The first one is pretty basic. The second one comes from this powerful thing called Gauss's law. But here's the trick. Since they're both describing the same thing, we can just set them equal to each other. We do a little bit of algebra, move some things around, and what pops out? Q divided by V. And hey, what did we just learn Q over V is? It's C, capacitance. We just derived the formula from scratch. And boom, here's what we get. This formula is a total game changer for engineers. It's basically a recipe for building a capacitor. You want more capacitance? Easy. Make the plates bigger. Or, and this is a big one, just move the plates closer together. This is exactly how we're able to cram so much power into the tiny components inside our gadgets. So we've got a handle on a single capacitor. But what happens when you start linking them together in a circuit? Well, it turns out their behavior totally changes depending on how you connect them, end-to-end or side-by-side. Pay attention to this, because this is absolutely key for any circuit analysis. When you line capacitors up in series, one after another, they all hold the same amount of charge, but the voltage splits up between them. Now, when you connect them in parallel, side by side, it's the total opposite. The voltage is the same for all of them, and you just add up their capacitances. It's that simple. And if you've worked with resistors, you'll notice this is completely backwards from how they work, which can definitely trip you up. And this leads to a super useful rule of thumb. If you ever need to get the absolute biggest capacitance you can, the answer is simple. Wire them up in parallel. Every capacitor you add just piles onto the total. Easy as that. Okay, storing charge is cool and all, but the real reason we use capacitors is for the energy they hold. So how do we figure out just how much punch is packed inside these little guys? So, take a number like 0.000075 joules. I mean, that sounds like nothing, right? It's an incredibly small amount of energy. But here's the thing. For a tiny component inside your camera, releasing that, 75 microjoules? Releasing it all at once is what creates that blindingly bright flash you need for a great picture. It's all about speed. And we've got a couple of go-to formulas to calculate that energy. Which one you pick just depends on what information you have. If you know the capacitance and the voltage, you use the first one. If you know the charge and capacitance instead, well, you use the second one. Both get you to the same place.
Here's a really cool example of this in action. Imagine you take a charged capacitor and dump all its energy into an insulated block, just heating it up. We can measure exactly how much the block's temperature goes up. From that, we know how much heat energy was added. And since all that heat came from the capacitor, we can set our electrical energy formula equal to the heat energy formula and work backwards to figure out the original capacitance. It's a perfect example of these formulas being used to solve a real problem.
All right, we've covered a ton of ground, but there's one last really important trick that lets us squeeze even more performance out of a capacitor. And the secret isn't in the metal plates themselves, it's in the empty space between them.
And that secret ingredient is called a dielectric. Now, it sounds fancy, but it's really just an insulating material, like plastic or glass or ceramic. But when you slide it into that gap between the capacitor plates, it does way more than just keep them apart. It basically supercharges the entire device.
So why bother with the dielectric? Well, for a few huge reasons. First, it massively increases the capacitance, letting it store way more charge for the same voltage. It also, of course, physically separates the plates. And maybe most importantly, it lets the capacitor handle much higher voltages before it, breaks. And we can actually measure this supercharging effect with a really simple number called the dielectric constant. It's just a ratio. It's the capacitance you get with the material divided by the capacitance you get with just empty space or a vacuum. So if a material has a dielectric constant of, say, 6, it means it boosts the capacitance by exactly 6 times. It's a straight-up multiplier. So let's do a quick recap of the whole journey. We started with the big one, Q equals CV. From there, we figured out where capacitance comes from with the physical formula. Then we saw how to combine them in series and parallel, calculated their energy, and finally learned how to juice them up with dielectrics. So that leaves us with a question. Now that you've got a handle on the formulas that govern this incredible rapid energy storage, what comes next?